Hello, welcome to Noise Control and its Management. Today is the last day of the 7th week of this course, and what we plan to do today is conclude our discussion on how to calculate the sound pressure level at a distance r, which is away at a distance r from a sound producing source. The sound producing source is what we have discussed till so far is in an ideal situation. It is located in free infinite sized space full of air, and there are no reflecting surfaces whatsoever in this whole space. So, for this kind of a situation, the value of LP which we had discussed, we had developed that relation, and we will write that relation one more time. The relation is LP, which is the sound pressure level at the location of interest, is equal to the sound power level LW plus 10 log of Q, which I call directivity index. Okay. So, we had defined this directivity index is 10 log 10 of Q, and please note that Q is a function of frequency. So, it can change with different frequencies, minus 20 log of the distance, how far the microphone is from the source, minus 4.343 mR plus or minus a constant number 10.9. So, this is in decibels, and DI once again I said is directivity index, and it is defined as 10 log of Q. I just wanted to do a couple of things in this lecture. So, first thing we will like to explore is what is the role of M in this whole thing. Okay. This is what we are interested in, role of M. So, the role of M is M we had discussed, either you can express it in inverse of meter, that is the unit, or in kilometer inverse. So, let us look at some of the values of M. So, I am just quickly going to write down this table. So, the first column is relative humidity, second column is temperature in degrees centigrade, and then we have different frequencies. So, 500, 1000, 2000, 4000 and 8000. These are central frequencies, and the first case is RH is equal to relative humidity is 20%, and we will see for two values 10 degrees centigrade and 30 degrees centigrade. So, what do the numbers look like? So, here M is in kilometer inverse, okay, 1 by kilometer, that is the unit. So, what do these units look like? 0.63, 0.52, 2.04, 6.98, 21.1, 29.9, 1.33, 3.58, 11.7, 24.3, and the other one 60% relative humidity. And again we will look at the value of M at 10 degrees centigrade and 30 degrees centigrade. So, what do the numbers look like? 0.38, 0.94, 2.51, 7.92, 15. So, it is 0.37, 0.88, 2.14, 5.43 and 9.01. Now, you would wonder what do these numbers mean. So, let us do some quick calculations. So, suppose there is a machine and it is generating noise, and it is, as we have discussed in this case, it is there in free space, infinitely large free space. So, it is just hanging in air and there are no reflecting surfaces, and the machine is producing noise, and the nature of noise is that it ranges between 500 to 4000 hertz. So, that there is a machine in space and it is generating a lot of noise, and it is producing noise at 500 hertz for all frequencies between 500 and 4000 hertz. And what we are interested, and suppose the microphone is located away from the machine, let us say r half a kilometer away from the machine. So, r is equal to half a kilometer, 0.5 kilometers. Then the question is, how much sound is attenuated because of this, because of air absorption. So, we have to calculate sound attenuation. Sound attenuation in decibels. This is what we are interested in finding it out. And then finally, we assume that temperature is equal to 30 degrees centigrade and relative humidity equals 60%. Okay. So, what do we do? So, sound attenuation equals how much? Minus 4.343 times MR in decibels. So, we will just make a quick table. So, for different frequencies we will see how much sound is getting dissipated by. So, F is equal to 500, 1000, 2000, 4000, and the values of M, what are the values of M we choose? We choose this row. Okay. So, values are of M are 0.37, 0.88, 2.14 and 5.43, and attenuation in decibels. How do we calculate it? We just calculate this term 4.343 times M times R, and R is equal to how much? 0.5. So, we are taking it in kilometers because M is given in kilometers inverse. If M was given in meters inverse, then we would have taken R to be 500 meters. Okay. So, this is important to understand. So, attenuation is 0.8 decibels, 1.91 decibels, 4.6 decibels and 11.8 decibels. So, what do you make of it? Essentially what it tells us is that at low frequencies, half kilometer away, sound does not get dissipated as much. 0.8 decibels is not a lot, okay. But 11 decibels or 11.8 decibels at 4000 hertz, it means that the power has gone down very significantly. Each time the power goes down by a factor of 10, you lose 10 decibels. So, the power which is reaching half a kilometer away is 11.8 decibels less, which is lesser than 10% of the power which was generated at the source at 4000 hertz. But at 500 hertz, virtually all the power is reaching out. So, at low frequencies, the effect of air is negligible. If you look at 100 hertz or 50 hertz, this number will be even smaller, it will be negligible. But at higher frequencies, especially beyond 2000 hertz, air acts as a very strong filter and it absorbs a lot of sound, but at low frequencies does not absorb a whole lot of sound. So, this is the second thing. And the last thing is that remember This relation is true for what? When the sound source object is located in free space and there are no reflecting surfaces anywhere around the thing. Okay. Now, what if there are reflecting surfaces? So, the question is, what if there are reflecting surfaces? What do we do in such a case? So, we will answer that question, and to answer that question, consider this experiment. Suppose I have a sphere. It is a perfect sphere and it is emitting sound, and it is in free space. It is in free space, and I am measuring sound at this location M, where I have placed a microphone. So, there are no reflecting surfaces in the sphere in the world, and I am measuring sound at this location, and I say that the value of sound pressure level here is LP, okay. And I will also put a letter N, which means in absence of no reflecting surfaces. Actually, let us make this sphere a little smaller so that it is manageable. So, it is a small sphere, and the sound which is being measured by microphone M is LPN, where N tells us that this is the sound pressure level when there are no reflecting surfaces. The sphere is hanging in free air and there are no reflecting surfaces anywhere in the whole universe, and it is LPN. Now, consider this: when sound is being emitted by this sphere, it is going in all directions uniformly. It is going in all the directions, uniformly in all the 3 dimensions, which means, what does it mean? So, now just consider this imaginary plane. Consider this imaginary plane which has been made in by a dotted line. It just is splitting the sphere in the top half and also the bottom half, right. The sound which is being sensed by this microphone M is because of what? Is it because of the top half or because of the bottom half? It is because of the top half. The sound which is being emitted by the bottom half is not going to this microphone at all, right. If there was some reflecting surface here, then it would reflect and come back, but because there is no reflecting surface at all, the sound only from the top half is reaching the microphone. The sound from the bottom half is just going in the other part of the universe, okay. So, I can also say that only the half of the sphere is responsible for producing this LPN. The lower half is not responsible for producing LPN, right. If there was another microphone here, then the lower half would produce LPN, but because the microphone is located in the top half, only the top half of the sphere is responsible for producing LPN, right. Now, consider another thing. So, now what I am saying is that here this blue line was a imaginary dotted plane which partitions the sphere into a top half and a bottom half. Now, instead of an imaginary plane, if I split this sphere into a top half and a bottom half, what will happen to LPN? Will it remain the same or will it change? Still, the lower half is emitting sound which goes to the lower half of the universe and it never comes back. So, it has no influence on the reading of this microphone, and the top half, the sound from the top half is still reaching the microphone, right. It is still reaching the microphone, and because of this the microphone reading is not changing. Everyone understood? So, what that means is that if I split a sphere into a top and a bottom half, the lower half has no influence, and I introduce a reflecting plane going through the center of the sphere, that has no influence on the reading of the microphone, right. Not because it is going through the center of the sphere. If the reflecting plane was here, then it would influence the reading, but because it is going through the center of the sphere, it does not have any influence on the reading of the microphone, which also means that instead, if I have a universe which has a top half and a bottom half plane, I do not need a whole sphere to produce the same sound pressure level, rather I just need a half sphere, right. I only need half of the sphere to produce LPN, because the lower half is not being utilized. Agreed? So, I only need half of the sphere to produce LPN. Now, if I have this type of a universe where there is a top half and a bottom half and they are separated by a reflecting plane, and in such a situation, now if I replace the hemisphere by a full sphere, in top half, what does that mean? That instead of a hemisphere in that, see initially right now in the top half there is only half of the sphere. Now what I am doing is I am putting the whole sphere on the top. I am putting the whole sphere on the top. What does that mean? That will mean that this thing will get twice as much as energy, right. It will get twice as much. See here it was getting energy which was sufficient to create LPN, only because only half of the sphere was there, but now I have put the whole sphere. So energy from here cannot go down, all that energy it will get multiplied because of this reflection, and the microphone receives 2 times power as received in case of half sphere, right. So in this case, if it gets 2 times as power, what will happen to this sound pressure level? It is 10 log of power divided by reference power. So LP, or you can also call it, so LP goes up by 3 decibels, okay, because 10 log of 2x, log of 2 is 0.3, so 10 times 0.2 is 3. So if I have one reflecting plane going through the middle of the sphere and the whole sphere is above that reflecting plane, then my sound pressure level goes up by a factor of by 3 decibels. Okay. Now this is only for one reflecting plane. Now consider another case. So you have no reflecting plane, and now I introduce one reflecting plane, but there is no reason I can also have another reflecting plane. An example of a reflecting plane would be, so you have one reflecting plane is this, another reflecting plane is this, and I have a sphere located here. In this case, and here I have my whole sphere is located here. If there was no sphere, only 1/4 of a sphere was sufficient to produce LPN, but now because I have put the whole sphere between the two reflecting boundaries, my LPN, now my LP, it goes up by how much? 3 decibels plus 3 decibels, because 3 decibels because of reflection from this surface and 3 decibels because of reflection from this surface. Do you understand this? So, this is when you have two reflecting surfaces and your object is close to the corner of the intersecting two planes. And finally, you could have even 3 reflecting surfaces. So, you can have this, this and this. And your object could be here. In this case, LP would go up by 3 decibels into 3 is equal to 9 decibels. What would be the physical situation? You have one reflecting surface, which is this ground, and the reflecting surface, which is a vertical wall. Third reflecting surface is perpendicular to it, and your sphere or the source is located at the intersection of all these 3 things. So, in absence of any reflecting surfaces, this is the relation which we use. If this object is placed on one reflecting surface, then all the energy will be prevented from going to the bottom half of the universe, and all that energy will again get reflected upwards. So, if there is only one reflecting surface, so this is when no reflecting surfaces. If this object which is emitting W watts is placed on one reflecting surface, then I have to increase my decibel level by 3 more, and if it is located at the intersection of 2 reflecting surfaces, then I have to increase my decibel level by 6 extra decibels, and if there are 3 reflecting surfaces like this, then I have to increase it by 9 dB. So, reflecting surfaces also make the sound more directional, because they reflect and send energy in a particular directional. So, just very quickly we will see one last slide for today, that because of the presence of reflecting surfaces also, there is an additional directivity factor. So, if it is in a free field means no reflecting surfaces whatsoever, then whatever LP we are calculating, that is fine from the formula which I had expressed earlier. If I have a flat plane and my sound producing object is located on that flat plane, then I have to add 3 more decibels. If it is at the junction of 2 planes, then I have to add 6 more decibels. And if my sound producing object is at the junction of 3 objects, 3 mutually perpendicular planes, then I have to add 9 extra decibels. So, what you have learnt is now that initially what we learned was how to calculate the sound pressure level in absence of any reflecting surfaces, and now if we, but remember, and now once we have reflecting surfaces, and remember when we say reflecting surfaces, they should be perfect reflecting surfaces. It is not that they are like sponge, that when sound hits they absorb some energy and only reflect a part of the energy. They have to be rigid walls, rigid flat shiny walls. So, whatever energy comes, none of that energy gets absorbed by the surface, all the energy gets reflected. if it is ground, soil and things like that, it is not a perfect reflecting surface. But if we have perfect reflecting surfaces, in presence of one reflecting surface, we add 3 to this equation. If 2 reflecting surfaces, we add 6, if 3, we add 9. But that is again the situation when we have perfectly reflecting surfaces. So, this gives you an overall idea how to compute LP in when the object is outside a room. In the next class, what we will do is we will do a similar activity and we will figure out how to compute sound pressure level LP when the sound producing machine, whose wattage is W watts, is located inside a closed room. So, that concludes our discussion for today, and we will meet next week. Till then, have a great weekend. Bye.